All right, guys, here's part two of that lesson for Thermo 2. So we talked about basically internal energy and just kind of did a bunch of the work, work and heat. Big thing is just knowing kind of, hey, what the signs are and stuff like that. But for chemistry, here's what really matters. All right, so here's you've all been in a chemistry class before, and you know that like, hey, we do stuff with open systems here. So you can see like, hey, these are open beakers. Okay, so it's an open system, meaning this, meaning that since it's an open system, we can eliminate pressure and volume since it's closed, and we can say this: the heat given off, which we call enthalpy, we'll get to that eventually, is the internal energy. So basically, in a chemist's crazy world, you can say this. You can say that the heat of a reaction is equal to the internal energy of a reaction. It's got to be what we call a constant pressure, which it is what it is. Okay, so all that previous lesson to say about work and energy is we don't care. It's just for you to get used to the symbols of heat and energy and work and stuff like that. Okay, so here's what really matters. Q of a reaction, I mean, it's an exothermic, it gives off heat. So if most of them are reactions are exothermic, they give off heat. When they break bonds, the energy released from breaking bonds goes to the surroundings. Endothermic would be that energy transfers to uh, the reaction. Okay, so there's a handful of things, like if you think about an ice pack, it's actually not the it's when you crack an ice pack and you put it on your hand, one of those cool packs, what happens is that ice pack doesn't it takes away the energy from your hand, right? So it's not, people think, oh, it's cold. Well, what it's doing is the reaction in the ice pack requires energy to be depleted out of your hand for that reaction to occur. So it needs to take energy away from the surroundings. So you got to think of energy as like an actual form of transferable matter that shifts and moves. So when you are doing a reaction that's exothermic, it's giving off heat and it's going to the surroundings. That's why things get hot. When things get cold, it's because energy is being taken away from the surroundings. That's that. If you've seen graphs like this, delta H is just another form of enthalpy, which is heat. An exothermic reaction would mean that like, hey, here's the nth, here's it before, here's it after. Where does this go? It goes out. Here's the reactants. Here's the products. Where does it go? It goes in. Stuff has to go in. So we care about enthalpy stoichiometry. You'll see like, hey, delta H is what we call enthalpy, and it just means heat. So if you look at this reaction here, hydrogen plus chlorine goes to hydrochloric acid, and it's going to give off 184.6 kilojoules of heat. All right, so how would I do this? If I want to figure out what like balancing would say is like if you had 1 mole and 1 mole of this, it's going to give off 184.6 kilojoules. That's kind of the base recipe, right? But I don't. I have 5.67. So we call this enthalpy stoic. I want to figure out if I had 5.67, if I produce 5.67 moles of this, how much heat is going to be given off. Okay. If I want to make 5.67 moles, how much heat is going to be given off, right? So what I do, they say 5.67 moles of HCl. Okay, well in 2 moles, because there's the 2, okay, there is negative 184.6 kilojoules. So basically what you do is you take this and correlate it to the coefficients. So 5.67 times negative 184.6 divided by 2 is going to give me negative 523.341 kilojoules. Now, why is that important? Because if you were to do a reaction and want to know how much heat is given off, you can calculate how much heat is given off. All right, let's go to our worksheet. I'll do the first one with you. Here's the reaction. The standard 224 tells me that negative 287 kilojoules is going to be given off. Well, if I want to find how much 226 grams of sodium oxide is going to, how much it's going to what's going to change that number? I have to do some stoic. So 226 grams of Na2O2. Okay, and I have to get out of grams and I have to get into moles if you're given grams. So grams for every 1 mole. And all I did was just add up 77 point, the mass of sodium, 2 sodiums and 2 oxygens. That's that number, Na2O2. Okay, so the next part then is I need to do my stoichiometric coefficients, and for every 2 moles of Na2O2, there is negative 287 kilojoules. All right, so I do the math, and I get 415 and some change. Negative 415 and some change kilojoules. So notice, what's the difference between these two problems right here? This one's in moles already, so I don't have to do this bracket. I can skip the grams to moles conversion. This one's in grams, so I have to convert it to moles, and then I can add my coefficient with the amount added there. So that's all that matters there. This one's in, when you do this problem, this one's in kilograms, so you just got to multiply by 1,000 to get out of kilograms into grams. All right, guys, do that. Check your answers. That is that learning target. It's kind of simple if you just plug and chug, but it's kind of boring as well. I get it. So, all right.